Welcome to our first attempt at a synchronous session in this asynchronous course. We're going to go through the first few items in the iteration module, talking about solution spaces and the way repetition is a tool for moving through them. So let's dive into the slide deck. So the first reflex is whether or not when you look at a problem, and this is a computational problem or a real-world problem, can you develop the reflex to say, I think that that could be solved by iteration or repetition? And what we'll see in a few minutes is that that in order to have that reflex, we have to have a sort of new and special understanding of what we mean by repetition and iteration. And then the second one is the capacity to look at a problem and to recognize that it might be actually a collection of a set of smaller problems. And sometimes this means a matter of dividing and conquering. And so the classic version of this is sort of a scientific method approach to fixing a car, say. So you bring your car in, you say, my car doesn't work. And I'd say, so how do you know it doesn't work? And you say, it's making a funny noise. You say, well, does the funny noise sound like it's coming from the back of the car or the front of the car? And you say, well, mostly the front. And so at that point, I stop thinking about the back of the car because you've told me it's probably in the front of the car. So I've just divided the problem in half. And then we say, does it sound like it's coming from the engine or from the body of the car? You say, oh, it's mostly the engine. So great, I've just divided it in half again. So one version of smaller problems is kind of a divide and conquer. Another one we'll see is when a solution really is a series of small problems solved, and we can add up all those small solutions together. And finally, there'll be another version where we can solve a very large problem by selectively going down certain paths and then backing up when we see that there's a mistake and so on. And you might recognize that from how you solve a maze. If you like to do mazes on paper, you typically follow out a path and then you hit a roadblock and you go back to the last place that looked good and promising and so on. So anyway, so these are what we're trying to come out with. And here's what we'll basically talk about. I'll hope to get this covered in the hour we have today. First thing is we're going to talk about what a solution space is, and then brute force approaches to exploring a solution space. And then there'll be three versions of that brute force. One is nested for loops, one is a repeat until, and one is a while do loop. And so those are the things we'll try to get covered today. Okay, so point number one, solution spaces. Is that a term that sounds familiar to anybody? Oh, good. Yeah, that's a good place where we've seen it. If you've done any linear algebra, you might have talked about spaces there. We're gonna start approaching it sort of with a fairly geometric metaphor, and we'll stick to 2 and 3 dimensions because we can visualize things there. Okay, so here's our first example. I'm going to make some soup, and I want to put some salt, pepper, and curry in it, and I want to find the best combination for these. So how do I go about solving this problem? So at the end of the day, there's going to be some amount of salt, some amount of pepper, and some amount of curry, which is going to be just right, which is going to make it taste great. Now, somebody might say to themselves, do you think there'll only be one combination that will be just right? And that's a good point, because there could be a really awesome soup that is very strongly flavored by curry and not so much by pepper. And there might be another one that's very strongly flavored by pepper, but only a hint of curry. So there could be more than one ideal here. But those ideals will consist of some amount of salt, some amount of pepper, and some amount of curry. And so we think of those as S sub right, meaning the right amount of salt, P sub right, the right amount of pepper, and C sub right, the right amount of curry. And so you can kind of think of these as each of them is a continuum. So we could have anywhere from, say, 0 grams of pepper up to 10 grams, 0 grams of salt up to 10, and 0 grams of curry up to 10 grams. And let's just imagine that where the arrows point right now happens to be a good solution to the make this soup problem. So what we're going to try to do is now we're going to say, can I think about that in a different way? And so what I'm doing here in this animation is taking these 3 linear dimensions and putting them together to create a 3-dimensional space. So think of this as, you probably remember X, Y, and Z from geometry. So where is the perfect soup? So let's look at another version. So we go out so far out on the pepper axis, and then we go over a certain amount on the salt axis, and then we go up a certain amount on the curry axis. And so we end up, this green spot, which is the good soup combination, is sitting somewhere up there in that space. So when we talk about a solution space, I want to say a solution space is all of the points, salt, pepper, and curry. And in this case, I'm considering anywhere from 0 grams of salt to 10 grams and 0 of pepper to 10 and 0 of curry. So it's a 10 grams by 10 grams by 10 grams space of soup ingredients. And we're suggesting that there's at least one sweet spot there, which makes a great soup. And that's where that green ball ends up out there in the middle. So the reason I call it a space is because it ends up looking like this box. So if I think 10 on each side of this cube, and then the different corners of the box can be characterized. So out here at the far corner, that's maximum pepper, maximum curry, maximum salt. Over here, it's high pepper, high curry, no salt. Over here, it's no pepper, no curry, no salt, and so on. So you can kind of see that every point in that box is a different combination of spices for the soup. And the problem of making soup is really the problem of exploring that solution space. So we want to move around inside of that solution space in order to try to find the best combination for the soup. Okay, so point number 2, problem solving can be thought of as traversing or moving through a solution space. So if you think about the way that you make soup, you stir in various ingredients and then you put in a little salt, you taste it. You put in a little pepper and you taste it. You put in a little curry and you taste it. And your brain, if you're a decent chef, will say, that's a decent amount of salt, but I think it needs a little more salt. And so the act of putting a little more salt in is moving a little bit of distance on the salt axis. So you're moving through the solution space to another salt, pepper, curry point in the solution space, and you're now going to try that. So can anybody think about one of the challenging things about cooking that might not be a problem in other kinds of problems and other kinds of problem solving situations? So let's think about when I've got my pot on the stove and I'm putting in some salt, putting in some curry, putting in pepper, and then I think, oh, it needs a little more salt, maybe a little more. What can happen there? And you're allowed to answer acoustically too. You don't just have to use the chat. Any suggestions? Yeah, you can't undo it. You can't erase it, right? So cooking, one of the things you have to do is you have to proceed in very small steps when you traverse the solution space, right? And when we later talk about artificial intelligence and machine learning, one of the things we'll talk about is the step size that you move through a solution space with. And if your step size is too small, your model will take forever to train. If your step size is too big, it's very easy to miss the good solution. So you can easily say, oh, it looks like it needs more curry. Let's pour in a pound of curry. And you go, well, we just broke the model because that clearly took us right outside of any possibility of finding the right solution. Okay, so traversing the solution spaces. Now the next question comes up is traversing the solution spaces and looking for what? Right, so we're in a solution space, but what are we looking for? So in the case of the soup, we're looking for that soup that tastes really awesome. But again, think about a little bit of a challenge when you're cooking. So you put in some salt, you put in some pepper, you put in some curry, a little bit more curry, a little bit more salt, maybe some more salt. And then you think, this is great, this tastes good. So what you found is a satisfactory soup recipe. But notice that you don't necessarily know if you have the best soup recipe, right? Because what you've done is you've sort of stopped at a place where it tasted pretty good. You're ready to go with it. You're willing to put it on the table. But it could be that there is some secret combination of salt, pepper, and curry that you haven't thought about, you haven't tried, that would be 1,000 times better. It would just be the ultimate soup of all time. So what are we looking for? So we can think of it this way generically, that when you traverse a solution space, you're either looking for the biggest reward or the smallest error or a satisfactory result. So the biggest reward and the smallest error are similar in the sense that they're both optimal solutions. In other words, they're the extreme version. You're saying if there's a highest or a lowest in there, I want to find that. Okay? But they're different in the sense that the highest reward, this can be just kind of bonus points that you pick up as you go along. And anybody who's ever played, say, Super Mario is familiar with this, that you can reach up and grab those gold coins in the sky along the way. And in playing that game and trying to come up with the ultimate play, right, you just keep trying to play it and compare how many points did you, how many rewards did you get last time versus this time. The smallest error is a little bit different in the sense that that suggests that we're comparing to something else. Right, so a smallest error says, I'm trying to make something, and each combination of inputs that I look at in the solution space, I want to say, how close is that to the target that I'm after? And then the last one, satisfactory result, I've got some standard, and so I'm going through the solution space and I'm trying to find a combination of inputs that gives me that that meets that standard, right? And so this is, for example, how a lot of us go to school, right? We say, I want to earn a B+. And so we try to figure out how much homework, how many points on each exam, how much time should I put into my projects in order to get enough points that's going to get me a B+. And after that, I'm fine. I'm not going to search for any more, right? Somebody else might say, no, I'm going to go for an A+. And they could do the same thing. But neither of those, in a sense, is the biggest reward, because somewhere out there, there's a learning that's like 5 times over an A+. But our whole school system is basically built to make us never seek that reward. Okay, so if we have a solution space, which is a geometric space where each point is a combination of inputs, and if we say we're looking for the point, the location in that space that gives us the biggest reward or the smallest error or a satisfactory result, that implies that each point in the solution space has a quality. Right? So that if that space we looked at before was X, Y, and Z, each point, right, it implies that for every single one of those points, there's a value that says this is how good the soup is at that combination. Does that make sense? We'll have to figure out an easy way for people to say yes to that. You can click on the hand raising or something. Okay, so every point in the solution state has a quality. So let's look at an example. We're gonna say what does our soup look like. So if I have no salt, no pepper, no curry, maybe the taste is a 2 on a scale of 0 to 10. If I have no salt, no pepper, a little bit of curry, maybe it's a 3, and so on. So you can imagine assigning a taste or a quality to every combination of inputs. And of course, the inputs could be finer grained than this, right? You could have 0.2 grams of salt and so on. So here's a simpler version. Let's imagine I'm going to Tim Hortons and the person behind the counter, when I offer some coffee, says, so how do you take it? And I'm supposed to say how many milk and how many sugar I want. And suppose for me, this is the way it works out, that getting 0 milk and 0 sugar is kind of blah. I'm not much into black coffee. 1 milk and 1 sugar scores a 1. So you can see on the chart here in 2 dimensions, right? I'm taking that list on the right-hand side of the page, and I'm putting it into a table. And each square in the table is essentially a point in my solution space. So what kind of coffee do I like? Anybody see how I take my coffee? What am I going to order when I go to Tim Hortons? No double doubles. You can tell I'm a non-linear coffee drinker here, right? And in fact, I must admit I'm lying here because I don't take sugar. I was just pretending to be someone else. But we can see that the highest scoring coffee here is 3 milk, 1 sugar. Now, I can visualize that. The shots. See, I'm a very boring coffee drinker. I'm just getting plain old coffee out of the drip machine. So the surface on the right-hand side here, and I couldn't quite get the shading right, but you get a little sense that at the axis that goes left and right in the picture is milk, and the axis that goes front and back is sugar. So there's a peak up there at 1 sugar in and 3 milk over. So the 0, 0 is in the far corner where we can't see, and then you see the abyss of 2 milk, 2 sugar. So this is a thing we want to train ourselves to do, is to think of solution spaces as landscapes. Now, in order to do that, I have to cheat and think only in terms of 2-dimensional solution spaces, because our brains can't visualize 4-dimensional manifolds. We don't have a way of our mind can't see a 4-dimensional space. When we think of solution spaces as three-dimensional surfaces, okay, two of the dimensions, what we're calling x and y typically, the horizontal and the back and forth, those are going to be the variables, the input variables. So these are our ingredients that are going into soup. It's the milk and sugar here. It's the data that we're putting into a model. The vertical dimension, the height or the altitude or the elevation of the surface, is the quality. So at every point on the map, the landscape is either high elevation, meaning high quality, or low elevation, meaning low quality. And when you traverse the landscape of a solution space, what you're going to be trying to do is find either the highest point or the lowest point, right? Depending on whether we're looking for the highest reward or the lowest error. So far, so good? Okay. So the takeaway then is that real solution spaces are going to be very high dimensional, but we'll metaphorically think of them as two-dimensional landscapes. Okay? So what we have in mind is stuff like this. And there's our little problem solver there traversing that landscape. Now, if we were looking for high spots, so biggest rewards on this landscape, can you think of any challenges we might face? So look at where our little problem solver is now. So if we asked her, which direction do you think you ought to go in to solve this problem, remembering that she's trying to find the highest rewards. She wants to go up. So right in front of her, the ground seems to fall down, and right to her left, there's a little bit of elevation, and right to her right, there's a little bit of a hill. And if she goes backwards, there's a very steep hill. Right? But if she goes to her right, she'll go over a little hump, but then kind of start going back down again. And she's going to miss some of the high points that are behind her over there. So the problem in landscapes like this is that there are sometimes local high spots or low spots. So in other words, right where you are right now, you can clearly see what direction to go in to get immediately lower or immediately higher. But that may or may not be a global maximum or minimum. And so when we're trying to solve a problem in a solution space, one of the things we need to be able to do is to say, I don't want to get stuck looking at local spaces. Right? And it's not unlike the advice you would give to somebody who grows up in a small town in northern Ontario, and they join the local swimming team, and they're just great. They swim, they love swimming. They win all these races, and they just plan their life around winning the medals in their little town. And you might come along and you say, well, that's great that you're the champion of your little town, but as far as swimming goes, there are bigger fish to fry out there, bigger rewards out there, and so you'd be pushing that person to go beyond the local part of their landscape, where they can be kind of king of the hill. And you say, if you go farther afield, you might be able to be king of the mountain. So searching for solutions, taking a journey through the solution space and looking for high and low points. Okay? So you can kind of imagine us walking around like this, where you're just constantly walking on that surface looking for the best spots. Has anybody heard the phrase gradient descent? So in machine learning, one of the main ways that the algorithm tries to find a better set of parameters, a better set of weights for the model, is using a technique called gradient descent. A gradient in physics or math is the tilt of a surface. So at any given point, you can look at the surface and you can kind of say that if you move in a certain direction, this surface is going uphill at a certain rate or downhill at a certain rate. So the gradient is the measure of what's the rate of rise or fall in a given direction. And so gradient descent is where the algorithm is looking to find a minimum. You're trying to minimize an error. And so what the algorithm has to do is it lands at a point in the solution space, and then it has to say, which way should I adjust the ingredients so that I'm most likely to move in the direction of a better tasting soup? And we call that gradient descent, in the sense that you're trying to descend the gradient. You're trying to find low points in the landscape. Okay, so back to repetition. So our third point is that repetition is a way of traveling through a solution space and considering every option. Or excuse me, it's a way of traveling through a solution space. Brute force is a subset, and brute force is the one that says one way to do that would be to travel through the solution space and consider every option. So if you went to culinary school, you could imagine part of taking a class called How to Make Salt Pepper Curry Soup would be to prepare a small batch of soup with every possible combination of salt, pepper, and curry. And then we'll do a blind taste test and collect all the data, and we'll figure out what the solution space, what that surface looks like, and we'll figure out where the perfect sweet spot for that soup lies. And we would do it by considering every single one. We think of that as a brute force solution. Okay, so here's one of our first examples. So if we said, I have a list of numbers, and I want to find the largest one in the list. You say, so what's the best way to do that? Well, we could write the first number down, and then we go through and we look at each of the next ones, and if we see one that's bigger, then we'll just remember that one. And we just keep going through the list, and anytime we encounter a bigger number, we make a note of that one, forget the one we knew before, and then at the end of the list, the number that we're remembering will be the biggest one. Sound fail-safe? So try to sketch a flowchart for that, if you have a piece of scrap paper there. We can even say you could use these parts. And if you've got a copy of the slide deck, you could probably save yourself a copy and edit it. Everybody taking a moment. This is one of the real challenges of doing this remote stuff, right? Because in a classroom, I'd look out and I'd see when people started to look up at the ceiling or check their phones. But now it feels a bit like that movie Alien where they say in space, no one can hear you scream. Okay, so here's a version. We start at the green ball at top. That's the beginning, the go. And we say, let's just pretend that the first number is the largest. And then if there's any more numbers, because if we have a list of just one, then obviously that one number is the largest. So if there are more, I go off to the left, and I'm going to get the next number. And if the next one is bigger than the largest one, then I'm going to say, oh, now that one is the largest. If it's not, then I just continue. And then I go out the bottom of the flowchart there and swing back around to the gray circle. And I ask again, is there any more? If there are, then I get the next one, test it, and so on. Now, what am I trying to do by putting a pink dotted line, a pink box around some of this flowchart and a blue box around some of the other parts of the flowchart? So, long story short, we're revisiting what we did in the flow and modularity. And so IN says there, deferring detail, exactly. I mean, in a sense, I've filled in the detail, but I'm showing you how I could defer the detail here, right? So I could think of this as, here's the way this algorithm works. Get the first number and treat it as the largest. And then while there are any more numbers, check the rest. And so the pink box would be check the rest. Right? And we say, well, how do you check the rest? And we say, well, oh, that's easy. You get the next one, and then you deal with it. And so the blue box is deal with it. And we say, well, how do you deal with it? Oh, you want more details. Okay. The way you deal with it is you compare the next number to the largest one so far. If it's bigger, you make a note of it. And that's it. That's how you deal with it. And so there's 3 steps of stepwise refinement in that picture. Okay, now we want to have a different challenge. Let's say we're looking for the largest number in a grid. So it's not just a list, but now it's a 2-dimensional grid, right? So it might be if you were scanning over my combinations of coffee combinations from earlier, right? So when we had that grid, so I want to write an algorithm now which will scan across so not the headers, right? There's the 2 rows at the top and there's the 2 columns on the left, and that's just the labels. But the data itself here is 0, 1, 2, 3, 1, 0, 2, 3, 6, 2, 0, 1, 0, 3, 1, 1, 0, 0, 0, 0. So what's my algorithm going to be for scanning that solution space and taking note of what the largest value is? So let's go back to where we were. Right. And so here we're going to proceed stepwise. Right? We say, well, similar to last time, we'll first make note of the very first number we see, and then and we'll pretend that's the largest for now. And then we'll say scan the grid. But then we say, well, okay, but how do you scan the grid? Right? So in pseudocode, we'd say what we're going to do is we're going to scan top to bottom, and we're going to scan left to right. And our rule will be if the item we're looking at is bigger than the one that we've had as the largest so far, then we'll make it the new largest. So the inside part is the same as last time. And so now we expand the scan the grid part to say, are there any more rows? If so, scan the row and then go to the next row. And our question would be, well, how do we scan the row? And so we're going to expand that out. And so we say, look at the largest. Are there more rows? And then we go in and we say, are there more columns? If there are more columns, then we compare. And then we go to the next column and we go around. And we come back in, are there more columns? And so the question, are there more columns? This is moving left to right across the grid. Right? When we get to the end of a row, the answer to are there more columns will be no. And so we leave the green part and we go out to go to the next row. And what did compare mean? So compare meant just if the item's bigger than largest, then largest equals next. So we had that 3 levels there. Now that description, and I think there might be a mistake in my flowchart back there. So if you're looking at this last part and go, wait a minute, you didn't go back to the top to the next row. That's correct. I'll fix that before I send the slides out. The pattern that we call that a raster pattern. And so raster pattern is when we scan across left to right and then go back to the beginning of the line, scan across left to right, go back to the beginning of the line, and so on. And if you've ever watched an old-fashioned television, the kind that maybe some of you have never actually seen, this is the principle behind the way TVs used to work. Is there was a electron gun behind the screen which swept over the screen in a raster pattern, and it did this like 30 times a second, and it would turn on or off depending on whether the pixel was meant to be illuminated or not. So this is a sort of a famous pattern in electrical engineering. So we've described how that would work. And it goes, if you were writing the JavaScript, you might write something like this. So the for statement in JavaScript takes 3 parts. We start out saying, what's the initial condition? So here we'd say for row equals 0. And then what's the stopping condition for row is less than the number of rows? And then how are we going to behave for each iteration? And in this case, the plus plus is what we call the increment operator. And so that says each time we repeat this, add 1 to the variable row. And I'm then going to, inside of that repetition, I'm going to put a second one. This one says for column equals 0, for as long as column is less than the number of columns, then increment column. And then I'm going to do some action on the data that's at row and column. And that action might be something like compare it to the largest so far, etc. So any questions on why that JavaScript produces the raster pattern? Suppose there were 10 rows and 10 columns. So we start out with row 0, and then we start out with column 0. So we're now at the data for 0, 0. That would be the upper left. And then we are now on the inner loop, and we're going to now go to column 1. So now we're still on row 0, but now we're on column 1. So we move over a little bit to the right. And then column 2, column 3, column 4, column 5, column 6, column 7, column 8, column 9, column. We don't go to 10 because we said there are 10 columns, and column equals 10 is not less than the number of columns. So at that point, we're done. And we bounce out, and we now go to row 1. And so that jumping to row 1 is that diagonal dotted line from the right-hand side of the top line over to line 2. See that on the diagram? It's called the horizontal retrace. So, anybody ever cut the grass in a yard? Rhetorical question. So when you cut the grass, you don't want to use a raster pattern because it's not very efficient. So if I cut the grass, I'm going to do something more like this. So I'm going to go along to the right, and then down, and then back, and then down and back. So I'm going to reverse directions each time. So let's think for a second about how we would write the code that would make us do that. So for the code for the straight raster was like this. So what's going to get us this? This is a stop and think moment. So here's the pseudocode for that. We say, let's loop over the rows, and let's loop over a row from left to right, and then let's go to the next row, and then let's loop over a row from right to left. And then we'll repeat that over again. So if we look at the diagram, that says we're going on the first row, we're labeled 15. So we go left to right, and then we go to the next row, and then we go right to left, and then we repeat that pattern. So we're next row, left to right, next row, right to left. Repeat that pattern. So what we have now is sort of a repetition of on the outside with a different kind of repetition on the inside. So a version might be like this. We're going to, start at row 0, do it for all the rows, scan left to right, go to the next row, scan right to left, and then down below we see what the finished version would look like. There's something new and a little bit weird in the last few lines. So the thing that's new here is we're adding the minus minus to do decrement because we're moving from the maximum number of columns backwards. So up here we started at column 0 and we tested for being less than the number of columns, and we incremented each time, and down in the last for loop we do the opposite. We start at the number of columns, we start at 10, and we stop when we get to 0. And the talent or the magic to doing brute force is making sure that you haven't skipped anything. And depending on the structure of your solution space, you're going to find that that's the challenge. Where the thing that they'll pay you big bucks for is for being able to come up with the method which will guarantee that you've considered all the options. Right? So if I'm in the kitchen and I say, find out what combination of curry and pepper and salt make the best soup, if you were just willy-nilly and you just tried a couple of combinations, we'd say, oh, that wasn't very smart. You didn't actually take a good brute force approach to that would consider all the possibilities. Now, can anybody think about a slight labor-saving device you might engage in when making that soup? So what if you had a theory that for spices, there's always an amount of spice, of any given spice, which is too much. And so you could do an initial experiment where you say, well, let's just try recipe with a little bit of salt and a little bit of pepper and 5 grams of curry. And it turns out it's terrible. And so you might say to yourself, great, we don't even need to look at the parts of the solution space that have 5 grams or more of curry in them. And then you could do a similar sort of thing with the salt and the pepper. There's going to be some amount of salt, which just turns out to be too much salt. Now, there's no guarantee that there's not a perfect solution out there that's 9 grams of each. But you can sometimes segment that solution space and make life a little bit easier. Okay. So the things that we've talked about here so far are the idea of looping over every dimension, looping over all the items in a list, or looking at all the different combinations. And we're just going to visualize the letter. So suppose I'm making something, and this time I'm not interested in how much of each thing, but just whether or not to include, say in this case, salt, pepper, and cinnamon. The cinnamon is either included or not included. And let's say that the upward branch is always included and the downward branch not included. And so if I have cinnamon, then I can either have salt or not have salt. And for each of those options, I can either have pepper or not have pepper. So you can see how this structure here allows you to specify every combination of cinnamon and salt and pepper being present or absent. This pattern is the same pattern we saw in truth tables. Right? So you could think of cinnamon, salt, and pepper here as just like variables A, B, and C in a truth table. And the combinations of them as you go along are just, it's like 1, 1, 1, 0, 0, 1, and so on and so forth. Okay, and then over on the side here we have some JavaScript code that describes that.